So now we should know about conservation laws, how they are formulated, what are the conservation laws that are considered to be generally valid, and we can go to study some examples and related material laws. Before going to actual material laws, some very generic truths about material laws and how they have to be written and formulated. The material laws have to obey some very general principles to be realistic and to be valid in our part of the universe, to say. First of all, the material laws have to be causal. This means that the future of a system cannot influence to the past or to the present. So whatever material property we are describing, the material property can depend on system quantities as of now or in the past, but never in the future. So we can't anticipate the future and make our material to obey the future. That's sort of forbidden. It would lead to very weird mathematical models. A bit similar is the requirement of locality. The laws we are writing, they have to be laws that are local. They are valid in the same points, not further. So the material property at point A cannot depend on anything that is in point B, which is of finite distance apart, because that would imply that there's infinite speed of propagation of information, and that will lead to a lot of troubles. So actually the laws are written for quantities or their derivatives defined in one point only. And that defines the model structure to a great deal. If we will have infinite speed of propagation of information, then we will get models that have more complicated structures and are more difficult to solve in general. But sometimes they are used as approximation because the speed of propagation can be extremely fast. Third general principle is objectivity. So the laws must be formulated so that they are independent of the position and movement of the observer or the coordinate frame, and that is already going a bit deeper. And historically, that was one of the requirements that led, for example, Einstein to discover the theory of relativity and the finite speed of light, because that was a requirement of objectivity in a certain coordinate frame that was behind. And finally, the most controversial or difficult or deep aspect is the thermodynamical acceptability, that the laws that we are writing, they must comply to so-called second law or second principle of thermodynamics that we will be discussing in a separate section. Now, back to the balloon. To understand the rising balloon, there are several phenomena that have to be modeled. We have to understand the forces that the balloon causes to the surrounding air or vice versa. So the balloon makes the air move around and this movement causes forces to the balloon, typically opposing the movement. How the pressure difference between the balloon and its environment will affect the balloon surface, maybe balloon shape, size, and so on. How the atmosphere behaves, how the pressure and temperature function, or they behave as function of elevation. We know that the air pressure is decreasing when we go higher, which means that the pressure difference between the balloon and its exterior is changing, and so on. And also what happens inside the balloon. What happens if the temperature changes, does the pressure change, and so on. There are a lot of things to be modeled. We'll start with maybe the simplest one, which is the temperature. So what are the main mechanisms for temperature inside the balloon? How does it change? What effects does the change have? Actually, I guess we don't go to the effects so much, but how does the temperature behave? There are several aspects that influence the temperature. Of course, the initial temperature of the gas, and the heat capacity of the gas, so that sort of causes the latency to reacting to external heating or cooling. Temperature outside the balloon, that tries to, I guess, balance the temperature inside the gas or inside the balloon, and thermal properties of the balloon skin. So these are the things that have to be considered, have to be modeled to have some idea how the temperature will behave. We will simplify the thing because the real balloon is three-dimensional and it gets to more complex notation. So in case you are not so fluent with three-dimensional notation and so on, we'll make this simple. So we will consider a one-dimensional crosscut. So just an interval from the center of the balloon to somewhere outside the balloon. So from A to, say, D. And we will have the balloon cover, the skin of balloon extending from B to C. So we have A, B, C, D starting from inside of the balloon to the exterior. To make things simple, we assume velocity as 0, so the balloon is not moving, and no internal heat source, so nothing is heating the balloon from inside. And we write the conservation law, okay, because the velocity is 0, the density is constant, so we don't have to derive the density, and the conservation of energy is written in a very simple form. So the total rate of change of energy of the whole system is basically the difference of heat flow on the two boundaries, so incoming and outgoing heat. So this is the energy balance. This can be divided to individual energy balances on different materials. And now we come to the material laws. The heat flux is typically modeled as being proportional to the temperature gradient, and the coefficient of proportionality is called heat conductivity. This is a material-dependent property, and likewise the internal energy is a function of temperature, a linear function involving a property called heat capacity, once again material-dependent. The different gases have different heat capacities, they have different conductivities, not to mention about the balloon skin, balloon material. T is the absolute temperature here, a new variable. So we have two laws and one more variable, and I guess we are close to closing the system. So we have E that can be written as function of T, Q is as a function of T. So we have everything as functions of T. So on each interval we can write the so-called heat equation, which is of this form. So it's a partial differential equation of parabolic type for temperature, having some material constants, C, K, having density that is assumed to be given because system is not moving, so the density is constant, and this is the equation. This is valid for each of the intervals with specific parameters for each interval. It's not pointwise valid on the whole interval because these properties, especially this K, is discontinuous, and here we are differentiating K when we are differentiating this for this parenthesis. So this is not well defined. So we can't just simplify this, or at least we have to define derivatives and much of the mathematics anew to do that. So in classical sense this cannot be written on the whole interval. On the other hand, on the interfaces this has to be continuous. Also the temperature has to be continuous, and we can eventually write a complex system of 3 partial differential equations and half a dozen of interface conditions on these interfaces, and we get the model that is well defined and can be solved, but it's a bit complex. And also there are some things that we actually don't yet know, we have to assume. For example, what happens outside the balloon and how far outside we have to go to know about it, and what we have to model. So let's go there. So in all continuum mechanical modeling, when we are working on the outer boundary of the system, we have to model the interaction of the system with its environment. So actually we need to write a model about the external environment to be able to derive the interaction terms on the boundary. For the temperature case, the easiest solution is to assume that we are far away from the balloon so that the balloon doesn't affect the environment, and we assume the temperature in the environment as known. So we have the temperature at this faraway point as given. Now to simplify, if we can assume that heat conduction is very high in the environment, so the heat conduction coefficient is very big, maybe there's heavy wind, air turbulence that is mixing the air very efficiently, and it's a good approximation that the temperature on the outer surface of the balloon is equal or very close to the temperature in the far distance. We maybe transform this condition to the boundary. Then we have one domain less to be considered in the model, so we only have the balloon inside and the balloon material, and everything that happens outside the balloon we will simplify to this condition. If this is a right way or not, that is something we have to eventually evaluate afterwards. It's a simplification, and it's maybe justified. Okay, the balloon material is typically very thin, so B and C are very close to each other, and because they are close to each other, we are integrating on a very short interval, so the total heat capacity of the balloon material is very small, at least for a big balloon. So we can ignore it, and once we ignore it and solve the heat equation in the balloon material, we get something like this. So as the heat flux has to be continuous, so this is the heat flux on the balloon internal boundary with heat conduction in gas, and this is the heat flux on the cover. So it has a different material property. The derivative is approximated by this difference, because nothing interesting happens on the short interval, and we get, okay, this Tc was fixed on the boundary, so we get something like this. So we get an experimental coefficient alpha, which is dependent on the material parameter, material thickness, which is the heat exchange coefficient of the balloon material. And now we have a condition for temperature at B, which is dependent on temperature at B and exterior date. So we don't care about the balloon material anymore. So we have been able to simplify the system to one heat equation with some complicated boundary on the outer boundary, complicated condition on the outer boundary. So this is how you can play around with models, make approximations, assumptions, and try to simplify things. We will not dig deeper to the temperature behavior at this stage, so we will go to the deformations. On the balloon surface, there are several forces. So the external pressure coming from the atmosphere, internal pressure coming from the gas inside the balloon, and then the forces that act on the balloon surface, because it's made of material that eventually will resist different forces. So there are forces in the balloon surface. It's normally a stretched surface. So some tension. So there's a pressure difference between inside and outside, because otherwise the balloon doesn't stay as a balloon. So there's higher pressure inside than outside. And this pressure tries to push the balloon in radial direction, which is stretching the length of the balloon material in tangential direction. and the material will resist this stretching and eventually create forces that will counterbalance this pressure difference in the normal direction. This is how it basically happens. Doing this properly in mathematical terms goes once again a bit too far for the time available for this lecture, so we will simplify things. So we will go to a simple situation that has nothing to do with the balloon anymore. So we have one-dimensional solid. It can be a metal string, a rubber string, or anything like that. So maybe a string. For 1D string, the equation of momentum is as was given in equation of conservation of momentum. Was given as conservation laws. Now we have the stress tensor tau that has to be defined. If the material is elastic, the solid elastic material, then typically the stress is proportional to deformation. So we have in 1D a very simple law where K is called the modulus of elasticity, and it's easily measured by applying a force to material and measuring the deformation. So this has been known for centuries. Now, to go further, we have to make some assumptions. So we will assume that the gravitation works in the direction of x-axis, so direction of the string. Velocities and displacements are also in the direction of the string. So basically we have a string that is hanging vertically in the gravitational field. It can be a long string with essential own weight, or it can be very short, and this is negligible, depends on situation. And then there are some conditions on the boundary, so we fix the displacement on one end to keep the string attached. So, and there might be, for example, some force on the other end. So having a weight on the spring, on a string or spring. And initial conditions. So the initial state, the deformations, velocities are to be given. And this is how we get an equation for a moving string or moving spring. Okay, let's go the balloon that is actually rising. So it's not just stretching around and not moving. There are once again different force components to be taken into account. We have the gravitation that is applied to the mass of the whole balloon and the gas. There is hydrostatic pressure from surrounding air to the balloon, and as the balloon is moving, the movement makes the air move around the balloon, and the air movement creates a force that applies to the balloon. All these have to be considered. The gravitation is sort of easy because we have a balloon with constant mass, so there's a constant gravitational force, at least if the gravitational field is constant. So if the elevations are modest, so that the gravitation doesn't change significantly during the movement, so we are not going to outer space or something. The lift to atmospheric pressure, it's locally constant. So if you are speaking of a few meters, if you go to kilometers, then things change. So, but locally, for defining the local velocity of rising, we can assume the atmospheric pressure constant, which means that the hydrostatic pressure and the force is also constant, at least for small times. But then what is left is the force due to air currents. These are not modeled so easily. What happens with the airflow and how does it create force to the balloon? So let's think of air that moves relative to the balloon. Maybe we will fix the coordinates to the balloon and assume that there's air flowing around the balloon with some velocity into infinity, and this flow will eventually create some force that applies to the balloon. We will consider the conservation laws of mass and momentum. So we have the law of conservation of mass, conservation of momentum. The balloons are typically moving slowly, and rather smoothly, so we assume that the movement is slow and even, and this means that the density and velocity can be taken constants with respect to time. That's why the time derivatives have been sort of smoothed out here. Now we have gas that we have to consider. So how gas reacts to force. The stress tensor for gas, or actually any fluid, also water and so on, behaves essentially in this way. It's proportional to the deformation velocity. So if there's a rigid body motion, there's no force. But if the motion is such that it deforms the material, then there's some force that is created, and then there's a pressure component in the force. We can normalize the pressure so that the pressure will eat out the gravitation part, so constant gravitation field and the hydrostatic pressure is resolved by this transformation, and what we are left with is this system of equations, which is called the Stokes equation for slow flow. It has two components. It has a component that says that the flow is incompressible, so the density is constant, which means that the velocities cannot behave freely, but they have to be divergence free, so they can't change the density, and that's the essential content of this law. And then we have this law that tells something about the velocity and pressure. This system can be solved with appropriate boundary conditions, and once it's solved, we can also solve the force that applies on the balloon surface. The force is something like this. So this is tau dot n on the surface. So these are doable. Maybe not during this lecture, but basically doable.